Bismillahirrahmanirrahim. Assalamu alaikum all. Welcome to lecture number 8 of Fundamentals of Electrical Engineering. In the last lecture, we talked about series parallel connections. We also talked about voltage division rule and current division rule. And we are actually understanding resistive networks where resistors are connected in different configurations. Today's lecture is going to continue on that topic. We are going to first uh, do some more series parallel circuit solutions. We are going to find equivalent resistance of a couple of networks, and then we are going to apply voltage and current division rules on different kind of other networks. So let's start. First of all, let's solve this circuit. In this circuit, you are asked to find the equivalent resistance as seen from the terminals A and B. And the equivalent resistance of this network, I'm going to solve that in a step-by-step manner. Let me show you that. So, the step number one here, let's write step number one. In the first step, what's going to happen is that this 1 ohm resistor and this 5 ohm resistor, they are in series, and I'm going to solve them together and reduce them into a single resistor. So that's one thing that's going to happen. In place of 1 ohm and 5 ohm, I am just going to have a single resistor. Apart from that, there is another thing that's going to happen, and that is going to be a very interesting and slightly unusual thing. You can see that this 4 ohm resistor and this 12 ohm resistor, they have one common node over here at the top, which is D, and another common node over here at the bottom, which is B. And both the resistors share the same two ends, and that means they are in parallel. This slight jump here, this thing is simply saying that the two wires are not connected. So actually the 12 ohm resistor has one end connected at D and the other end connected at B. This jump tells that there is no connection in between the 12 ohm and the 6 ohm resistor. So what's actually happening is that 12 ohm and 4 ohm are in parallel. So I'm also going to solve the 12 and 4 ohm in parallel and place the resultant where the 4 ohm resistor is present. So I'm going to solve these two. The remaining of the circuit is not going to change. So let me draw that. The remainder of the circuit is going to be same as before. So 5 ohm, this one is actually the sum of 5 ohm plus 1 ohm resistance, which means this one is 6 ohms. The parallel connection is 4 ohm parallel 12 ohm, so that this resistor is going to become 4 into 12 over 4 plus 12, and that results into 48 over, now let me do that with a calculator. So uh, so let me do that sum with a calculator. So 48 divided by 16, which results in 3. So this resistor is essentially 3 ohms now. Let me use a slightly broader marker. So 3 ohms. The remaining of the circuit is the same. This is the point D, and we have 1 ohm resistor over here. This is the point C in the given circuit, and you can also see the 6 ohm is also going to be there. So this is the 6 ohm, resistor, and this 3 ohm also is going to be present like this, no changes to the 3 ohm resistor. And finally at the end we have 10 ohm at the top and no resistor at the bottom. This is point A and this is point B. So this is how your circuit is reduced. Two things have changed. 1 ohm and 5 ohm are connected in series and have resulted in 6 ohms over here, this one. And this 6 ohm, sorry, this 12 ohm and 4 ohm are actually in parallel, and their resultant is this 3 ohm. This is the first step. Moving to the second step of this solution, we are going to again reduce the circuit, and let me do that here. So step number 2 of the solution, what can be done now? Now if you see the circuit in step 1, it's quite clear that the 3 ohm resistor and this new 6 ohm resistor are in parallel. That's very easy to see. Moreover, this 6 ohm resistor and this 3 ohm resistor are also in parallel. That's also quite easily understandable. So 6 ohm is parallel with 3 ohms and 6 ohms is parallel with 3 ohms. So let me do that reduction over here. So 6 ohm in parallel with 3 ohm, this is going to be one resistor at the end over here, and this 3 ohm is going to stay just like that, no changes to the 3 ohm resistor. This one is 6 ohms parallel 3 ohms. The 3 ohm is not going to change, and the connection is not going to change. It's just going to be like that. After that, this 1 ohm at the top is also going to remain there. But what's going to happen is that since this is one node and this is one node, 6 ohm and 3 ohm are going to be connected in parallel. So I can put them like this. This is 6 ohms in parallel with 3 ohms. And finally at the left side, at the top we have 10 ohms, and at the bottom there is no resistance. So this is A and B. What is 6 ohm parallel 3 ohm? Let's find that out. 6 into 3 over 6 plus 3, and that comes out to be 18 over 9, which is 2 ohms. So this one is 2 ohms, and similarly this one here is also 2 ohms. Let me clarify that. I'm going to erase this and write 2 ohms over here. So 6 into 3 over 6 plus 3 comes out to be 2 ohms. This is 2. This was step number 2. Moving to the third step, uh, let's see what's going to happen in step number 3. And in step number 3, the circuit is much more reduced now. This is 2 ohms and this is 3 ohms. Now the 2 ohm and the 3 ohm, since you can see they share the same node here and here, 2 ohm and 3 ohm are in parallel. I think that's the only thing you can do in this step. So much simpler step. The remaining circuit is going to look the same as before. I'm going to draw the remaining circuit first, and then this resistor now is actually 2 ohms in parallel with 3 ohms. The remaining circuit is same. So this is 1 ohm, this one is 2 ohms, and this is 1 ohm resistance. And these are points A and B. And 2 ohm parallel 3 ohm, what does that make? 2 into 3 over 2 plus 3. That comes out to be 6 over 5. So this is actually 6 over 5 ohms. That's what it is. Well, we can reduce it as a fraction. Let's do that, because you are required to give answers in fractions in this course. Give your answers in decimal points in this course. It's not good to keep fractions in circuits. So 6 over 5 is going to give you 1.2. So let me write that. Let me first erase this 6 over 5. And that 6 over 5 is actually 1.2 ohms. Now, I think only a couple of steps are still remaining. So in step number 4, let me bring that down even further. So in step number 4, uh, step 4, what we have is this circuit, and it's quite easy to solve now. This 1 ohm is in series with 1.2 ohms. So that's what's going to happen. And the remaining circuit is going to be the same as before. So 1 plus 2 ohms is going to give you, sorry, not 1 plus 2, it's actually 1 ohms plus 1.2 ohms is going to give you 2.2 ohms over here. And the remaining resistors are 2 ohms, and finally 10 ohm over here. Actually this over here is 10 ohms. So this is 10 ohms and A and B. We are almost done through our circuit. So in the final stage, in the very final step, we can see that hold on, we can see that 2 ohm and 2.2 ohm both are in parallel. So step number 5, 2 ohm parallel 2.2 ohm. So these two nodes are shared by 2 resistors, and they are in parallel. They are going to result in just one resistor, and that is 2 parallel 2.2. That is their equivalent resistance. We are going to find that out in a moment. And the remaining circuit becomes very simple. So just the 10 ohm resistor is left except for that. So A and B. And you can solve this again. 2 into 2.2 divided by 2 plus 2.2. What it's going to come out, let's do it on the calculator. So 2 times 2.2 is equal to this, and the answer is divided by 4.2. Oh, I'm sorry, this is not what I intended to divide. The answer is divided by 4.2. The result comes out to be 1.04. So I'm going to round it off 1.05. Well, I'm going to just use 3 digits. That is the right correct scientific method. So I'm going to write 1.047. Okay, so this comes out to be, this resistance comes out to be 1.047 ohms. And finally, in the very last stage, you can see that 10 is in series with this 10 is in series with 1.047, and I am not going to take another step. I am just going to write our equivalent is equal to 10 plus 1.047, and that results in 11.0 11.047 ohms. That is your answer. So our equivalent for this question, the answer comes out to be 11.047 ohms. Now this is one of the methods. You should practice initially with this method, step by step, reduce the circuit one by one, or two simplifications at a time, or one simplification at a time. Just find out which are in series, which are in parallel, and draw the next circuit. And in this way you can grasp the concept. There is another way of finding R equivalent, but you should only use that when you have much more understanding of the whole system. So let me show you that, so that you can practice that method also. I can write the whole expression of R equivalent over here. Let me use some other color. So I can write the whole expression of R equivalent by doing something like this. So R equivalent is equal to, let me show you the initial circuit, and that circuit is this. The left hand side, you can see that 5 and 1 are in series. So in this method I'm going to start from the very right hand side, and then keep on writing the expression and move towards the left, and finding out which are resistors are in series and which are in parallel. But you should be only doing this when you have much more experience. So 5 plus 1, the resistance 5 plus 1 is in parallel with 4 ohms. So that's the first part. Let me do that. So in the R equivalent expression is going to look like this. I'm going to start writing from here. So it's 5 plus 1 ohms in series. They are in series, but their resultant is in parallel with 4 ohms. Okay, so you can see that the resultant is in parallel with 4 ohms. The next thing is that's happening is that whatever the result comes out of that 5 plus 1 parallel 4, you have that result in parallel with 12 ohms. That's what's happening. So whatever the result comes out, that whole result is in parallel with 12 ohms. How can you say that? Well, look at the circuit over here. 1 plus 5 is going to be just over here in the same line. That in parallel with 4 is going to leave you with just one resistor, which would be actually in this place. And that 4 ohm, that resistor is connected between D and B. And the same is true for the 12 ohm resistor. It's connected between D and B. That's why this resultant resistor is in parallel with 12 ohms. Now once you have solved that, this branch is going to be eliminated. You won't have this branch anymore, and whatever result over here is in series with 1 ohms. Since this branch is going to be eliminated, this branch would be in series with this 1 ohm resistance. So whatever the resultant of this expression comes out to be is going to be in series with 1 ohm. What's happening next? You can see that after that reduction, you are just going to have one resistance over here in place of 1 ohm and 4 ohm, and that one is in parallel with 6 ohms. So let me go to the expression again. The whole thing is in parallel with 6 ohms. And finally, not finally, I think there is one more step. One more step is that whatever the resultant that comes out of that resistor that is parallel to 6 ohm is now parallel to 3 ohms, because 6 ohms and 3 ohms are in parallel. So this whole thing is in parallel with 3 ohm resistor. And finally, whatever the resistance comes out of this stage, it's going to be just a simple resistor over here, and that would be in series with 10 ohms. So in series with 10 ohms means the whole thing in brackets plus 10. That is the expression for equivalent resistance. How are you going to solve this parallel thing? Well, this is a shortcut of writing that whatever two numbers are present on the left hand side of the parallel sign and the right hand side of the parallel sign, you just take them like this. If you have this a parallel b, you just find out a into b over a plus b. This is the equivalent resistance of two resistances in parallel. This is how you are going to solve for the parallel sign. This is a shortcut that's mostly used in your textbook and other places. So that's just a shortcut. And this is how you can write the complete expression. But please, one thing I must clarify, that do not use this method unless you are fairly adept and competent in the step-by-step method. Okay, that's very important. Now let's take another example. I'm just going to give you some hints. So this is another example, and in this example I'm just going to point out which resistors are in parallel and which are in series, and you are going to see that it's quite easy. So step number one in this connection is that you can see this branch, this node and this node, these two nodes, they both have resistors 5 and 20 between them, which means they are in parallel. These two resistors are in parallel. This is the first step. At the same time, this same node over here and this node over here, between them you can see that 9 and 18 are shared, which means 9 ohms and 18 ohms are in parallel. So in step number one, what's going to happen is that you are going to get uh, for the top part, let me do that. For the top part, you are going to get one resistor over here. That's it. That's just going to be one resistance. You can imagine the 20 ohm resistor is gone now. So there is just one resistance in place of the 5 ohm resistor. 1 ohm is going to be there. This diagonal 20 ohm is going to be there. This 2 ohm resistor is going to be there. And in place of 9 and 18 ohms, imagine that 18 ohms is gone and you have just one resistor, which is 9 which is the parallel combination. And finally on the left hand side at the top you have 8 ohms, and at the bottom you have this line. So this is A and B. What is this? This is 1 ohm. This one still is 20 ohms. The bottom one is 2 ohms. This one is 8 ohms. The top one is actually 20 parallel 5, and this left one is actually 18 parallel 9. This was step number one. Step number two is simple again. This 1 ohm and 20 parallel 5 are in series. So instead of both the two resistors, there is just going to be one resistor on the right hand side, and its value is going to be 20. This resistor is going to be 20 parallel 5, whatever that value, plus 1. Okay, so these two are going to be replaced by one resistance. At the bottom you have 2 ohms. Again in the diagonal you have 20 ohm resistance, and this one is 18 parallel 9. So 18 in parallel with 9, and at the top you have 8 ohms. So this is how the circuit gets reduced. I'm not solving these parallels, so you can solve them for yourself. The answer is provided in the handout. Now in the third stage you can see that this 1 plus 20 parallel 5 and this 20 ohms, they both are in parallel because they are sharing the same two nodes. Both of their ends are connected to the same pair of nodes, and I'm going to reduce them into a single resistor like this, and this resistance is going to have this resistor is going to have a resistance 1 plus 20 parallel 5, the first resistance, and this whole thing is in parallel with 20 ohms because these two are in parallel. Okay, that's one thing. I think there is no more simplification left. So at the top you are going to have nothing, at the bottom you are going to have 2 ohms, and this vertical one is actually 18 parallel 9. You cannot also solve this at the moment, and at the top it's 8 ohms. So this is how the circuit looks like at this stage. In the next stage, uh, you can easily see that this resistance over here, this one, is in series with 2 ohms, and then the result is in parallel with 18 parallel 19 ohms. So I'm just going to first solve them in series. These two resistors in series, when you solve them, you just get one resistance, and the other one is this resistance, which is 18 parallel 9, and at the top you have 8 ohms, and at the bottom there is nothing, so A and B. This is how it looks like. This resistance, however, let me write it over here. Let me write it at the top because it's getting confusing. So this resistor, you can see that it's actually the the series combination of this one and 2 ohms. So let me write the whole expression. 1 plus bracket 20 parallel 5 bracket close, the whole thing in brackets parallel 20, the whole thing in brackets, and it's in series with 2 ohms plus 2. So this is that resistance. And in the final two stages, what's going to happen is that you are going to take this whole resistance and take it in parallel with 18 parallel 9, and then simply add 8. So let me write it over here for your reference. You can solve it later at your convenience. So there it's going to look like 1 plus brackets 20 parallel 5, this whole thing in brackets parallel 20, and then plus 2, and the whole thing in parallel with 18 parallel 9, and everything in series with 8. So this is one of the methods of solving series and parallel equivalent resistance circuits. Um, you can take a look at the notes, and I've provided some other hints and methods also. Please do that and practice these methods, because this is one of the very foundational techniques that we are going to use in this course. One important note about series parallel combinations is that well, there are certain kind of series parallel there are certain kind of combinations which you cannot say that they're either series or parallel. For example, this circuit. So in this circuit, if you try to solve it using series parallel networks, actually you are not going to be able to do that, because there is no parallel circuit over here. If you think that this 20 ohm and 15 ohm are parallel, no, they are not. Similarly, this 10 ohm and 2.5 ohm, they are also not parallel. None of them are parallel, even though this looks like a parallel kind of combination. And in order to start solving this circuit, you must understand that there are uh, certain uh, um, certain connections or configurations that are neither series, neither series nor parallel. And there are two specific cases. Well, I'm just going to quickly throw that to you. So there can be a certain circuit that looks like this. Imagine that this is a circuit, this is R1, this is R2, and this is R3. This kind of a circuit is called a T or Y connection. This is neither series nor parallel. Similarly, if you have this kind of a circuit which is present over here, you can see this. You can see this is not parallel. Similarly, this kind of a circuit, if I draw it like this, and it has one node over here, one node over here, and one node over here, and let's call them RA, RB, and RC. This kind of a circuit is called a pi or delta network, delta connection. And this is also neither series nor parallel. And there is a method of interconverting these networks. For example, you can convert um, a Y connection into a delta connection, and similarly you can also do a conversion from delta to Y, but you cannot convert them into series or parallel. So these conversions are actually out of the scope of this course, and hence we are not going to study them, but you should know that in some of the circuits there might be conditions where there is neither series nor parallel combination, and in that case these kind of circuits, the T or Y connection or the delta connection or the pi connection, their interconversion helps you in solving equivalent circuits. You must understand that. The next topic that I am going to discuss in this lecture is simply the application of voltage division rule and current division rule. Uh, we have studied these two rules, and we must realize that we can find voltage, current, and power in series parallel circuits using VDR and CDR. Before I start solving these circuits, let me remind you the key points. The first key point is that you need to use VDR and CDR in these cases. You need to remember their formula. The second key point is that you need to be careful when you assign current directions and when you assign voltage polarities. They should be in accordance with the VDR and CDR circuits that we have studied. Sometimes it's also helpful to do some series parallel simplification before starting the solution. So these three are the key points for these kind of circuits. We are going to be solving very simple um, resistive circuits. So this first one, for example, is very simple, and you can easily see that this is the total current I in terms of current division rule. This I is actually spreading into three different branches. One is this 5 kilo ohm branch, let me call it I1. The other is this 20 kilo ohm branch, let me call it I2. And this third current goes into this left hand side 1 kilo ohm and 3 kilo ohm branch, let me call it I3. You see that I've already started with the current division rule, because it's quite simple to use the current division rule when you have a current source. You have one current actually supplying the power. So current division rule is naturally going to be used over here. However, the circuit does not ask you to find currents, but it actually asks you to find voltage V1 and V2, which are the voltages of the 3 kilo ohm and the 20 kilo ohm resistors respectively. So how are we going to find voltages when we are actually applying current division rule? The answer is very simple. After applying the current division rule and finding out the resistances, finding out the currents I1, I2 and I3, we can easily find out the voltages using Ohm's law. Ohm's law is always going to be used in circuit analysis. The second part is simple. What is the power dissipated? So that's very simple. Once we have the voltage and once we have the current, we can use this equation and find the power dissipated in these two resistors. The third part asks you to find out the power supplied by the current source. What is the total power supplied by the current source? Well, there are two methods to do that. I'm going to use the simple one, which is voltage across the current source, V current source, multiplied by the current. And remind you that this is going to be a negative sign power because the power is being delivered since the current is leaving here the positive terminal. Let's quickly solve them. The first one is V1 and V2. We need to find these two voltages. Now V1 voltage is over here, plus and minus, and it's actually related with I3. Let's find out I3 first. So applying current division rule for I3, it comes out to be I3 equals the total current I times, in the numerator you are going to write 1 over R3, and in the denominator you are going to write 1 over R1 plus 1 over R2 plus 1 over R3, and this whole thing is a factor. Now if you want to quickly look into this, it's quite simple. R3 over here is actually the series combination of 1 kilo ohm and 3 kilo ohms. So R3 here in this expression is going to be 4 kilo ohms. What about R1 and R2? R1 is going to be, you can see over here, I1, the resistance with I1 is 5 kilo ohms, and R2 is going to be the resistance with the current 20 kilo ohm resistor. We can plug in these values and in this expression. Remember that I is simply 10 milliamperes, so we can plug in these values and we can find out the value of I3. Once we find out the value of I3, since I3 is flowing in this branch, it's also flowing through the 3 kilo ohm resistor. We can easily find out V1 by the expression V equals I3 times 3 kilo ohms. So let me first write the value of I3. You can check it yourself. I'm just going to write it directly. So the I3 value comes out to be 5 milliamperes, or 5 into 10 to the power minus 3 amperes. This is the value of I3. Similarly, since we have the value of I3, you can see in the circuit that I3 is flowing in this way and it's going through the 3 kilo ohm resistor. And since we have the current of the 3 kilo ohm resistor, we can find out V1. And the value of V1 is going to be simply the current flowing through it, which is I3, times the resistance that it has, which is 3 kilo ohms. And if you substitute the value of I3 over here, what you are going to get is V1 equals 15 volts. That is the first part of your answer for part A. Now similarly, if you want to find, let me segment this a little bit better. So if you want to find the current flowing in the 20 kilo ohm resistor, because you need to find V2 and V2 is over here, then if you want to find V2 you need to find I2. So I2 can be calculated using the formula I2 equals I multiplied by 1 over R2 division 1 over R1 plus 1 over R2 plus 1 over R3. And through this formula, if you supply these numbers R1, R2 and R3 inside and I equals 10 milliamperes, what you are going to get is I2 equals 1 milliamps. And if you use this value of 1 milliamp, you can easily use the Ohm's law to find out the voltage V2 across the resistor 20 kilo ohms. So using Ohm's law, V2 is going to be simply I2 times 20 kilo ohm, and that is actually going to be equal to 20 volts. So V2 is 20 volts is the second part of the answer. Now after the first part, it's the part B over here, after part A, part B over here is very easy to find. You can simply supply the values of since you need to find the power dissipated in part B, you can use the formula P equals V times I. The power would be in positive because it's being consumed by the resistors. So the 3 kilo ohm resistor is going to consume a power which would be simply V1 times I3, and the 20 kilo ohm resistor is going to be consuming power V2 times I2. The answers are provided in the handout. Please do that calculation and verify. Now part C is interesting because in part C you don't need to calculate any other thing. You just need to see that what is the power supplied by this current source. The easiest method is that you find out the voltage across this current source. Now if you look carefully, this current source and this 5 kilo ohm resistor and this 20 kilo ohm resistor, all three are in parallel. Therefore the voltage across the current source is the same voltage across the 5 kilo ohm resistor, and that is the same voltage across the 20 kilo ohm resistor, and we have already found it. So the current source has a voltage of V2 across it. So the power of the current source is equal to minus times, since the current is leaving here the positive terminal, the value V2, since V2 is present across the 5 kilo ohm resistor as well as the 10 milliamp current source. So minus V2 times 10 milliamps. And the answer, again, please do it yourself, can be verified through the handout. So you can see that current division rule is easily implemented in circuits to find out voltages and some other currents and power consumed and delivered by different elements. I have this other example here. I'm just going to give you a peek of this example, and then I'm going to conclude this lecture. This is also a very simple example where you're asked to find voltage V1, which is over here, V2, which is over here, and then currents I1, which is flowing through the same resistor as V1, and I2, which is flowing through the same resistor as the voltage V2, and the power dissipated by the same two resistors. Now this is your example. You might ask what to use here, and since you have a voltage source, the natural way of going here is to use the voltage division rule. But the problem is that this circuit is not in series. So these two resistors are in parallel, 12 and 6 ohms, and then 10 and 40 ohms are in parallel. The easiest way to solve this, let me give you the hint, is to reduce these two top resistors, 12 parallel 6, and then these two right hand resistors, 10 parallel 40, And now apply the voltage division rule. So uh, this voltage would be V1, this voltage would be V2, and the current is going to be I. And now apply voltage division rule to these two series connected resistors. Once you do that, the problem becomes very simple, because V1 is the voltage that is present over here, and it is the same as this V1. Similarly, V2 is the voltage that is present over here across these two nodes, and it is the same as the 40 ohm resistor voltage. And once you have found the two voltages, once you have V1 and V2, you can easily find currents I1 and I2, because I1 and I2 can be found using Ohm's law. And once you have done that, you can also find the power dissipated through these resistors, P equals V into I. I would urge you to solve this numerical on your own. The answers are present in the handout. Let us meet again in the third lecture, where I'm going to introduce you to an even broader technique of circuit analysis. Until then, Allah Hafiz, and thank you very much.